9 to 12. But anyway, so we won't spend too much time on this. I think I took 40 minutes already. So let me hand over the time to Kevin Meng, and he is the speaker of today.
Cool, yeah. Hey, everyone. I hope you're doing well. Today, we're going to be diving into a fun problem. Today, I'm not going to do much talking at you as opposed to just doing things along with you. So we're going to be looking at a problem from USACO from a couple of years ago, I think about 4 years ago. And we're just going to solve it together. I haven't really looked at it before, so you're going to see how I think through problems, and I'll get to see how you guys think about problems as well. We'll be working together on it. So here's how it's going to work. I'm going to share my iPad screen, and we'll talk through the problem, and then you guys maybe can suggest some potential solutions. And yeah, it's gonna be fun. So let me go ahead and share my screen. Cool. So I hope everyone can see this. I think you can. Let me just go ahead and mute this. And this is our problem. All right, give me 1 second.
Make sure mute. Mute.
All right, cool. So just so I can get a gauge on you guys, how many people have not seen this? If you have not seen this problem, go ahead and react with a thumbs up in the Zoom like this. And if you have seen it, feel free to let me know in the chat, and then maybe we can talk. Okay, so it seems like most people have not seen it before. And I'm not getting any messages about having seen it, so I think we're good. Cool, cool. And it's good. I was just seeing if you guys were around. So it's good to see that you're all here. Cool. So let's read the problem first. I think we'll just read it. We'll sort of annotate the problem and just look at what parts are important. So here's the deal. Farmer John has a bunch of cows. Some of them have spots and some of them don't have spots. He's just taken a course in genetics, and he's convinced that the expression of the trait where cows have spots and don't have spots are caused by a single location in the genome. So this is like a super bad oversimplification that computer scientists have made for genomics. But basically what they're saying is, if you have a string of DNA that looks like this, they're saying that at one position of the DNA, so here they have, we have positions 1 all the way through m positions, and they're saying that at one of these positions there is a the genetic code will dictate whether this cow has spots or not. And we'll look more closely at this, but basically the idea that these people have is your genetic code, as you might know, is built up of 4 types of bases, or 4 types of components. We'll just say for now, there's A, T, C, and G. So these components are what define you, are what give you all of your traits and everything. And what this problem is saying is that, at every position you have either A, T, C, or G. Like here, cow 1 has A, cow 2 has G, cow 3 has G, etc. And you have M of these positions. And they're saying that, at one of these positions from 1 through M, there's going to be a determination of whether this cow has spots or not. Cool. So let's keep reading. So it says that Farmer John has sequenced the genomes of his cows. So he's found all of these DNA sequences. He says each genome is a string of length M built from the 4 characters A, C, G, and T. So this is where the computer scientists just abstract away biology, and they say, assume that the DNA just is made up of these 4 characters, and this is true. So then he builds this table. So this is a table of all of this is the genetic makeup of all of his cows. He's got 6 cows, 3 of them are spotty and 3 of them are plain. And he's got all of their M positions in their genome all mapped out. He knows exactly what they are. Cool. So what's next? It says he's looking at the table, looking carefully at the table. He surmises that position 2 is a potential location that could explain spottiness. So I think this is a really important part of the problem that if you don't understand, you have to look more closely at. So let's look at this. Let's look at position 2. Why would position 2 be a good indicator? So it says, by looking at the character just in this position, Farmer John can predict which of his cows are spotty and which are not. And if you look at it more closely, you can sort of intuitively understand this. You know, maybe it's not totally clear how you would compute the validity of position 2 as a candidate for a spottiness explanation, but intuitively you can sort of grasp it, right? Because if we look at all the spotty cows, the DNA base in position 2 is either A or G, right? So you've got spottiness, and you observe that only you observe AAG. So your conclusion is that A and G, if you have A and G, then you're spotty, at least in these cows that he has. And then you look at all the plain cows and they all have C. So your conclusion might be plain, then we have C, right? And so does anyone want to explain, maybe in more formal terms, more specifically why this is good and maybe what would be a case that's bad? So why does this distribution of spottiness and plain cows, why is this good for us? I think Alvin's raising his hand. Yeah, feel free to unmute.
Because like on position 2, the genomes for spotty and plain cows are all distinct.
Yeah, exactly, right? They're distinct. Like so I think maybe a term that we can use to describe this is they don't intersect, that's absolutely correct. That's the right answer. And we can maybe see this more clearly if we look at a position that is bad. So let's stop looking at position 2 and let's look at some other position. Let's look at position 1. So maybe our hypothesis is that position 1 is a candidate position, right? And we look at all the spotty cows. So the spotty cows have A and G because you have A, G, G. And if we look at the plain cows, you just have a bunch of A's. This is bad because A is found in both plain cows and spotty cows. So this is strange because then if you see an A, you don't know whether the cow is spotty or plain. So basically you can boil this down to, this problem is asking us, well, let's just keep reading. So let's keep reading. It says, he surmises that position 2 is a potential location. So what we know so far from what we've read is that potential locations, you're going to want to look at the sort of set of characters that are at that position and determine whether or not they intersect or not. And that'll tell you whether it's a potential location. But we haven't finished reading the problem yet, so let's keep going. Given the genomes of Farmer John's cows, please count the number of locations that could potentially, by themselves, explain spottiness. So pretty simple task. Basically, what it's saying is we should be going through all the positions and figuring out whether each of these locations independently can be a potential location. And like what Alvin said, all we have to do to check whether this is a potential location is to see if the spotty cows and the plain cows have different sets of characters, have different DNA bases that are at those locations. And if there's even one intersection, then that's problematic because then if we observe an A, for example, in position 1, if we see an A, well, we know that this A appeared in the spotty cow, but also A also appeared in a plain cow. So then we wouldn't have enough information to figure out whether it's a spotty or a plain cow. So yeah, that's the problem. It seems pretty straightforward. So let's keep reading. We got to figure out what the input format is and what the output format is. And given this, we can maybe sketch out an algorithm that we can use to solve this. Cool. So the first line of the input contains N and M. Remember, N is the number of cows, and M should be the number of positions. And this is important. Both positive integers of size at most 100. So this is going to be less than or equal to 100, and this is less than or equal to 100. So the next N lines will each contain a string of M characters. This will describe the genome of that specific cow. But But note this, it says n lines contain the genome for the spotty cows, and then there are n more lines that define the genomes of the plain cows. So in total, you're actually going to be reading in 2n times m characters. Because if you imagine, you're going to have n lines that are for the spotty cows, and each of them is going to be m characters. And then you're going to have n more n plain cows. And you're going to have m characters. So if you imagine you're calculating the area of this big rectangle, then you would just have 2n times m. So that's how many inputs we have. I mean, so if you look at this example, then n is equal to 3 and m is equal to m, whatever that is. Cool. So does this make sense to anyone? Does anyone have any questions at this point? Okay, awesome. Cool. All right. So let's brainstorm an algorithm that we can use to compute this. But first of all, I guess maybe it's a better idea if we just look at the sample input and we run some calculations. So this sample input is with n equals 3 and m equals 8. So remember, this is n and m. Remember that these are the spotty cows because this is the first 3, and then these are the plain cows. So let's draw a line here so that we don't mess ourselves up. And let's figure out what the answer should be, and let's check it against the official answer. And so you guys are going to help me do this. Let's look at the first location. So let's look at this first location. If you think that this is going to be a valid position, react with a thumbs up. And then if you don't think it is, then react with a thumbs down. So just think about it. Cool, I see some video thumbs downs. We also have some thumbs ups. It seems like thumbs down is the dominant answer. Does anyone who voted thumbs up want to explain why they think it's thumbs up? So how about someone who voted thumbs down? Okay, someone's asking for a link to the problem. Sure, I'll send it. Okay, Leo's got me, thanks. Yep, that is the correct problem. Okay, so Alvin wants to go. Yes, Alvin.
Because both spotty and plain have A, so that means
exactly.
that like you can't like say that, oh, if it's A, it's spotty, but if it's A, it's also plain. So it's kind of like that doesn't work because both of them have A.
Right, exactly. So we can't formulate a decision boundary. You have A on both sides, so that's problematic. So that's good. We can draw an X here. The first position is bad. Now I'll just go through the second position. The second position is good because we have AAG and we only have C's on this side. So this is going to be good. Or we can use green to notate this. And then I'll just tell you that for the rest of them, we have problems. So for the third position, we have T's on both sides, which is bad. So this is an X. We have C's and T's on both sides for this one. So that's bad. We have C's and G's on both. This is bad. C's all on this side. That's bad. A's all over here. That's bad. And then T appears on both sides here, which is also bad. So in the end, what should we return? Does anyone want to just throw it in the chat? What is the answer we should return for the program? Cool. So we have some ones, we have some twos. For the people who said 2, would you mind explaining? If anyone wants to type an explanation in the chat. Okay, the misclick. Yeah. The correct answer is actually 1 because the output format is asking you to just count the number of positions, an integer in the range 0 through m, where you could have possible explanations. And so we only have 1 here, so we should return 1 and print it out. Cool. So we've basically manually solved it. We know what procedure we should take. We should just iterate through all the positions and figure out whether each position is okay. But I think it's probably worth thinking about how we should do this computationally, because it's very easy for you to do it if you have just 3 cows on this side and 3 cows on that side. But if you get more and more, this will start to become problematic. So let's think about an algorithm that we could use to solve this. And notice that we have to do a complete search over the entirety of the M positions. So this is like position 1 all the way through M, which is 8. So we have to search through all positions. Is the algorithm that we run at every single one of these positions the same, or is it different? And you can, again, just type your answers in the chat if you have any ideas. Are we going to be using the same or the different algorithm? Yeah, I'm seeing a lot of sames in the chat. We also have some difference. Aaron, would you mind explaining why you think it's different? I mean, you totally could be right. Oh, okay, he says never mind. Okay. So I'm sure that you could approach it differently. I don't think that would be the best way to do it. So let's think about it. Why is it the same? For someone who said the same, does anyone want to explain why you think it would be the same? It doesn't have to be a complicated explanation. Yeah, okay, so Jefferson and Dylan have some comments about saving time. So yeah, exactly. You could put a for loop around the entirety of the M positions and just run the same piece of code at the same time. So yeah, fundamentally, these are the same problems. Every time at every M position, you're solving the same problem. And they're also independent of all the other positions, because you're essentially just looking through all the characters at that position and seeing, do I have more than one, do I have any occurrences that are bad? And so it's really the same thing again and again. So we should just use the same algorithm, put a for loop around it, and either write a function or just put the code inside the for loop to do the checks. Cool. So given that we know that we're using the same algorithm for all M positions, we should already acknowledge that basically we're going to be putting a for loop around all the M positions, and we're going to run some code, do something with the position. And this code that right here that we've defined here is the algorithm that we want to write. This is the key part. For any given location, without loss of generality, we can choose one of the locations. What is the code that we should write to check whether they're conflicting or whether this is a valid position? So this is going to be the pseudo code that we need to write here. So we should write a function. We should say, I'll put it in pseudocode format. We'll convert it into App Inventor later. So this is a function. We can ask, is good position? And it'll take in an integer position, POS. And so this will be our function. This is the code that we're going to write. So what exactly should we be doing here is the question. Does anyone have any ideas using some data structure that we've learned in the past, whether it be a map or an array or any sort of computational structure that we can use? Oh, okay, so Leo has an interesting question. Why wouldn't it be I is less than 2n and not I less than m? So Leo, do you want to explain basically how you're thinking about the problem right now? And maybe we can figure out what the conflict is between what we're thinking. So if you think about it, so this is, I admit, this is kind of confusing. You have 2 axes. You have a big grid of letters. And the question is the problem the same this way, or is the problem the same this way? So which way do you think it is? Do you think it's option 1 or option 2? And feel free to unmute if you think it's easier to talk that way. Cool. Yeah, it's all good. No worries. I think this is a good question. So let's talk about it a little bit more. So Leo, basically, if you look at what we've been doing, we have M positions, and it says that for every M position, we have to check whether it would be a valid, whether it's going to be a valid explanation position. Does that make sense? If it makes sense, just indicate that in the chat so I know. If we agree up to that point. And if, feel free to say no, and then we can talk about it more. Or in other words, the premise of the question is that you have all of these positions and you want to figure out, you have all these M positions and you want to figure out which one of them is going to be a valid explanation for spottiness or not spottiness. Does that make sense to you? Yeah, okay, so that makes sense. So what did we just do to verify that this is actually true? We basically went to every single position, right? And we looked, we said, out of the spotty cows, what are we going to be doing? We're going to think about, you know, we have all these characters and we want to know whether these characters overlap with these characters. So we went down a column, right? So that was to solve the problem for one column. But you're going to be repeating this procedure again and again, right? You're going to be doing it for this column, and then this column, and then this column, and then this column. How many columns do we have? We have M columns, right? So that's why we have M columns, exactly. So we're actually about to get to what you said. We're going to be doing a loop over 2n, but we haven't quite gotten there yet. That's when you solve the problem itself. But we're actually solving M independent problems. M as in like May. We're solving M independent problems. So I hope that helps. And that maybe that shows you why we're doing an M loop here instead of 2n. We're going to be going to every one of the columns and we're going to be solving the same problem. Cool. Yeah, that was a really good question. And I'm sure that other students had it. Props to you for actually asking. Does anyone else have any problems regarding just the premise of what we're doing here before we dive into the function that actually solves the problem per column? I'll give people a second to sort of gather their thoughts. And then Jason, I promise I haven't missed your message. We'll talk about your idea. Okay, great. I think we're all caught up. Thanks again for asking this, Leo. But let's move on. Let's consider what Jason said in the chat. So I'm going to pull it up. It says, make a list of the letters in the spotty cows, do the same with the plain cows, and see if there's any overlap. So yeah, I think let's roll with this. Let's see what we can do with this. So if we go back to an example and say that, you know, we're looking at position 1 again. Let's use position 1 as our candidate. So what Leo is saying, what happened to my screen? So what Jason is saying is, what should I do? Let me clear this out so we can talk. So Jason says we should make a list 1. So let's create a list. So this is list 1 and list 2. And he says, make a list of the letters in the spotty cows, do the same with the plain cows, see if there's any overlap. So I'm going to ask a clarification question. How do you want to construct this list? Do you want to iterate through all these positions and just throw them into a list? Or what do you think we should do? What kind of list should this be? How many elements should be in the list? How should we construct it? And anyone else, feel free to jump in on this too, because we're on the right track, but there are just a few more details that we're missing before we get to the right answer. So I'll just say this. I think that making a list of things is a very reasonable idea. And now the question is, what should you put in that list? If anyone has any ideas, or maybe if Jason wants to suggest something, feel free to throw it in the chat. Okay, so Leo says we should just have one big 2D list with everything in it. So that's basically what they give you, right? They give you a big 2D list of things with everything in it. And this is one of the sort of central questions in many computing problems you'll ever encounter in your life, which is, how do I represent my data? Because there's going to be a lot of different things that you need to represent, and different forms of data representation have different advantages. If you think about, I don't know, you guys have probably taken tests before at school. You for sure have taken tests before, but I don't know if you guys have taken tests that are open note, where the teachers allow you to bring all of your notes with you so that you can use them on the test. I think this is less common in elementary school, but when you get to college, there are a lot of teachers that allow you to do this. But the question is, do you copy your entire textbook and bring it to the test, or do you basically boil down all the important information into maybe a smaller representation that you can bring? So there's a big conflict, right? Because if you bring the entire textbook, you're going to have all the answers. Is it like taking notes for Sci Ollie? Probably, right? Like taking notes, do you write down every single detail that you can, basically copying down the textbook? Or do you want to transform the representation into something that is better, right? And Leo says, obviously no. Because on the test, even though you're going to have all the answers, you're not going to have time to search through all this information and just get what you want. And so it'd be much smarter to boil everything down, to transform it before the test, and to compact the knowledge. So any form of representation of knowledge goes, as long as you're not losing information. Like if you wanted to keep the representation in a big 2D list, you could, but it's not going to be the smartest thing, because all the information that you have, it's too complicated. It's not in a good representation for processing. And that would make things a little bit more challenging. And basically you want to transform the data to sort of, you want to massage it to fit what you want. So now Leo is suggesting 2 2D lists. Interesting. So 1 for each type of cow then. So we're getting closer. So now you have 2 lists, and now these 2 lists, you have the added guarantee that in any single one of these lists, all the cows are the same type. They're either spotty and either plain. So we're making progress. But one thing I'll say, Leo, before I move on to the other student suggestions, is think about whether you actually need a 2D list, because we've been given in this problem statement that all these M positions are all independent. They don't depend on each other. So think about whether you can compress it down to 1D. But that's actually sort of where I'm going with all these other things. So we've got 2 very interesting sort of opposing trains of thought, I think. So Ambrose and some other people propose all the elements in the plain cows, and all the elements, I'm guessing, in the spotty cows as well. And then Jason suggests a max length of 4. There's has A, has T, has G, and has C. And I think one of these is a little bit better than the other. Let me read through all the other responses and I'll just collect them. List of the columns. A 1D list with all the columns of the plain cows, and another one with all the spotty cows. Cool. Yeah, so let me write out all these suggestions and let's compare them and see which ones are better. So let's just call one of these representations proposal A, proposal 1. So let's call this proposal 1, P1. So the first proposal is that we take these things and we just throw them into a list. So we have A, G, G, and we have A. So this is going to be our list. This is proposal number 1. We have a second proposal. There's P2, and we have list 1 and list 2. So the second proposal is actually quite interesting. So I think Jason is the only one that suggested it. I think everyone else is on proposal 1. So P2 says we're going to have 4 elements. What just happened? We're gonna have 4 elements. We're gonna have 1, 2, 3, 4, 1, 2, 3, 4. And we're going to represent it in such a way. We're going to say that each of these represents A, T, C, and G, A, T, C, and G, A, T, C, and G. And we're just going to put a value that's a Boolean. We just need one thing. We just need one sort of Boolean. We just need to know whether A appears in the spotty cows and whether A appears in the plain cows. So we're going to look at it and say, okay, so A is here. So definitely this appears. This is a 1. T does not appear in the spotty cows. So this is going to be a 0. C does not appear. It's going to be 0. and G is going to appear. So it's going to be at 1. And then if we look at these cows, then it's just going to be A is 1 and everything else is 0. Does anyone want to vote? Which one of these representations looks much easier to deal with, to find the correct answer with? Yeah, right? P2 is really nice. We're going to have to think more carefully about how we can find P2, but if we can compute P2 efficiently, it's really nice because all you have to do is look at the columns. If you see any index with both of them equal to 1, then you're in trouble. So yeah, I think Leo is on the right track. 2 is really nice, but how do you make such a thing? It's a little bit tricky. So there are a lot of different ways we can make it. Let's talk about all of them. But for now, I just think that I think I should bring up 2 things. First of all, is this representation is nice. It's a little bit tricky to make, but representation 1 is actually still viable. And I guess this would be a good time to talk about time complexity. If you were to look at P2, how many comparisons would you have to make out of these things? Does anyone want to make a proposal? How many things would I need? How many comparisons would I have to make, basically? Yeah, so Ambrose and friend with no name say that the answer is 4. And that's exactly correct. So no matter how big our list is, we're going to have 4 comparisons. We have to compare the first one, the second one, the third one, and the fourth one. So actually, this is what we call O of 1 time complexity. No matter how many cows you have, this is as big as it gets. This is really nice. O of 1 is great because imagine that when we're dealing with computers, usually the problems we're thinking about are the ones where we have a heck ton of cows, like millions of cows. And if we had anything that was, if we had a million cows, we still would only have to do 4 comparisons, which is really nice. But let's think about how we could use representation 1, proposal 1. This is still a viable representation. But here's what you would have to do. You would have to go to every single element in list 1. So you would basically go say, okay, I have an A here. And then you have to go through every single element of list 2 and see if it matches any of the ones in list 2. So you would have to go, does A match A? Okay, yes, it does. So that's bad. Does A match A? Yes, it does. That's bad. Does A match A? Okay, it does. It's bad. Then you would have to go, does G match A? 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 So if you notice here, how many computations have we done for these 3 things? How many comparisons have we had to make? We had to make 9, exactly. And if you think about it more carefully, this scales quadratically. So this takes O of n squared time. But I think a few of you clever people out there might be thinking, well, what the heck are you doing? This is a complete waste of time. Because once you've seen that the first A matches, you could just return no, right? And how many comparisons will we do in that case? We would do 1, right? So what is the deal? Does anyone want to propose like what the deal is? Because in some cases we're doing really, huge amounts of work, and in other cases we're only doing 1. Exactly. So Leo's got the idea right. I think Leo was the only one in the when we asked the other question to give a minimum and a maximum bound. So this is a really, really important this is a very important thing that you need to do. It's a very important frame of thinking that you have to have in computer science, because you're always going to be able to find cases that are very efficient for stupid algorithms, because you just have a nice scenario. But as Leo says, we have to think about the worst case scenario. There is a very simple way to construct a worst case scenario. Does anyone want to propose what this is? There is a way of constructing scenarios that is always going to be worst case. And it's very simple. Does anyone want to give a stab at what it is?
Make it a match.
Yeah, exactly. So make it so that you'd never have any conflicts, right? So let's say that you had TTT. Oh shoot, this is like a bad color. Let's say we had TTT down here and we had ACG. You're never going to match any of these. So you're going to have to search through all n squared before you can actually you can actually solidly conclude that there are going to be no conflicts. So in any case where you have a valid proposal, a valid candidate for determining spottiness, you're going to take n squared time. And as Ambrose says, if you have 1,000 counts, then you're going to have to do 1,000,000 computations to determine this. And what if you had 1,000,000 m's? What if m was 1,000,000 too? That would be bad, because then you would have to do this amount, lots of zeros amounts of computations. So this is really, really bad. N squared is a bad thing. We want to keep most of our algorithms at least linear. So this is n squared in the worst case. And O of 1, the thing about this is that it's O of 1 in the worst case. So no matter how bad our situation is, we're not going to have to do much work. And although, like, you know, I've spent a lot of time sort of milking this idea of worst case and best case and thinking about complexity, but it's not going to be a huge deal when you do bronze level problems, but it'll become very, very important when you move on further in your careers, in your CS careers and beyond, because scale is one of the hardest things to deal with in the real world. If you think about the number of people that are using Facebook right now, or the number of people that are using Zoom, it's on the order of millions. And think about if we had 1,000,000 people and an n squared algorithm, that would take a huge amount of time, 10 times to 10 to the 12, just operations that we would have to do for you know, if we wanted to do the operation for all the people working on Zoom. And that's intractable. It blows up very, very quickly. So the efficiency of your algorithms is going to be an important topic, an incredibly important topic. And within this school of analyzing the performance of your algorithms and designing them is this idea of worst case performance. Just because there is a case where your algorithm won't fail doesn't mean that it will never fail. And one of the most valuable things that you can do in algorithms, you can win big prizes and get lots of recognition for doing this, is to prove that your algorithms will never be very expensive, will never be very slow. And that is an incredibly important and difficult thing to do. So, you know, in the context of bronze, it's not a huge deal, but I just wanted to show you guys the difference that it can make. Maybe for your future endeavors, if you want to go into computer science, it's going to be an important topic. So obviously we want to select proposal 2, but I think lots of students had questions, right? Like, how do we compute proposal 2? Because here's the deal. This time complexity is only the time that we have to use to make our decision after we've constructed these representations. What if proposal 2 takes O of n squared time to actually create? Because this is not straightforwardly created from our algorithm. So if it takes O of n squared time to create this representation and then O of 1 squared time to solve it, we still have a quadratic algorithm, and that's bad. So we need to make sure we can construct this representation very quickly. And so that's what we'll look at now. Does anyone have any ideas as to how to compute this, how to create this arrangement of lists in an efficient manner? If you have any ideas, feel free to just throw it in the chat. And if you're confused, just react with a thumbs down so that I know maybe where everyone is. But I'll give you guys a few seconds to think about it. So I think we've got a really good amount of ideas. So, I mean, let's just go through them one by one. Aaron is definitely right. We're going to need if statements, but there's actually a way where we don't need if statements, and I'll show you guys how to do that. But I think Ambrose has the most interesting proposal. I think it's very close to being correct. So what Ambrose proposes is we have to check each element of the list, and we run an if statement. We say, if, or we iterate through all the 4 characters. We iterate through A, B, C, and D, A, T, C, and G. So let's write it out here. If we have AAG for spotty. And we have AAA, I think it was, for plain. So what we can do is we just look at, so first we look at all the A's. So then we just iterate through the spotty. Is there an A here? Yes. Yes, there's an A here. So then we put a 1 here. So A, T, C, G, these are just the elements of the array. Then we just look at the T's. Is this a T? No, it's not. Is this a T? No. Is this a T? No. So we put a 0. If for C's, is this a C? No. Is this a C? No. Is this a C? No. Then we put a 0. Is this a G? No. Is this a G? No. Is this a G? Yes. This would be a 0, 0, 1, 0, 0, 1. So, and this algorithm is good because why? Jason has said exactly why it's good. It's O of 1. It's O of n. Because we have to iterate through all the cows. We have to iterate through all the n cows. And how many times are we iterating through all the n cows? So Dylan says m times. So technically you're right, but we're going to be doing this whole thing m times. But how many times for each run of the algorithm do we need to run through the cows? Do we just need n, or do we need more than n? So what did I just do here? We went through all of the characters and we scanned through all of these, right? So Dylan's right that we have 2n cows actually. But let's just assume, okay, so we have 2n, that's right, that's the first multiplier, but we're not quite done yet. Do we just do 2n operations? Remember what I did? I looked at A, I iterated through all of these. I looked at T, I iterated through all of these. I looked at C, I iterated through all of these. Ah, yes, that's what I was looking for. So Jefferson says we need to do 8n, and that's the correct answer. And why is that? We have 2n cows, and for each, we have to look at 4. So 2n times 4 is 8n. So Jason is right that constant factors don't matter in big O notation, but I'll say 2 things here. First of all, big O notation does not mean practicality. If you think about it, if you have an algorithm that takes 4 days to run, if you can reduce the constant factor by a factor of 8, then it will take half a day to run. So even though we don't care about constant factors in big O notation, they're practically important. And that's sort of why I wanted to mention this, because there's an algorithm that we can use that actually takes only 2n operations. So while this definitely does not make a huge difference for algorithms that can run in less than 100 milliseconds or so. But as you'll see, if you do USACO in the future, you might be able to bring your submissions under the time limit just by making constant factor optimizations, which is pretty interesting. But I hope, does this make sense to everyone why we have to take 8n operations? If it makes sense, just please react with a thumbs up in the chat so I know everyone's following. And if it doesn't make sense, feel free to react with a thumbs down and then I'll explain it again. Cool. Awesome. All right, so we have 8n operations that we have to do. Can we do better? And so I'll propose an algorithm that you can use that only takes 2n. Leo says you're just looking for match right in the 2 lists. Yeah, you are. So the algorithm that I will propose goes as this. You first initialize the 2 lists to just all zeros. And for every single thing, you have a mapping. Let's say that A maps to position 1. So this is position 1, T maps to position 2, C maps to position 3, and G maps to position 4. All you have to do is iterate through each one of these lists. And at each one of these indices, you just say list at the index for A is equal to 1. And then here we just do this again. We just say list at index for A is equal to 1. And let's do this one more time. List at index, this one is going to be index for G is 1. So what have we done here? When you do this, you're going to go to the list at index for A, and that's going to be this index, and you're going to set it to 1. this is going to be it. It's just going to be 1. And notice that we have this property where once something is set to 1, can it be set back to 0? Yes or no? No, right? And that's exactly what we want, because we just care whether this character appears at least once in the list. So this is actually good. This is sort of a, this is basically equivalent, like Jason says, to breaking out of the loop. It's a little bit different, but we're basically maintaining a property that never changes. And we never want this property to change. And so then we're good. So basically we've done this for the first one. If we do it for the second one, we're going to see something interesting. If we do it for the second one, we already set this to 1. So when we set it to 1, it doesn't change anything. And then when we do it for the third one, index for G is going to be the 4th one. So we're going to set this one to 1. So notice that we've only iterated through the list once, and then we have 2 n's. So we're going to be doing a total of 2 n operations. But this is better than 8 n. If originally the algorithm was going to take 8 hours to run, 4 hours to run, now it's going to take 1 hour to run, which is great. That's a 4 times improvement in the performance. In USACO, it doesn't really matter because these algorithms are designed to run in less than a second. So a factor of 4 isn't a huge deal as long as you're not doing anything crazy. But just keep this in mind. Constant factors can be important, even though they're not included in big O notation. Cool. Does this make sense to people? If you have any questions, feel free to ask. Or if you don't, then just thumbs up again so I know that we're all following. This is probably a more confusing part, so definitely feel free to ask if you would like a re-explanation. And if this feels a little bit strange, first of all, just don't worry, because it's just something that you pick up through experience. And then second, we'll be implementing this in a second. So not to worry if it just looks a little bit strange. Cool. So before we get started on the coding, so let's just write out the algorithm that we should be using. So the first thing is you'll want to read in everything into, let's say, a list of strings. So we're going to say, so let's just say that we have a variable that's called, what should we call it? Genome. And we're going to read in, read input. And so this is going to be a list of strings. And what we need to do is for I in the range 0 to m minus 1, we're going to say solve. We're going to say solve I. So we're going to solve I. And then we're going to need to define another function that's called solve. So function solve. Okay, so this is actually, let's call this is good position. Function is good position takes in a position. And this is called this, function solve. So this is the main function. And right here, we're going to want to call is good position I. And what we're going to do in good position is we're going to create. So let's just say we have 2 lists. We have list 1. We're going to assign this to create. Let's just call this an existence list. We're going to be giving it I, and then we're going to say list 2 is going to be, we're going to create another existence list. But let's just say that this one is for spotty. This one is plain. And Ambrose, yes, you can do this. Let's see. I think I understand what you're saying, but I'll come back to this. And it probably, so it doesn't make any asymptotic difference in the runtime, or not even just any comparison difference. It saves a little bit of time for saving these lists, but it's not a big deal. So I'm not going to worry too much about it. But yeah, if I'm understanding what you're saying correctly, basically you're saying you can just create the first list and then just iterate through the second list without creating this existence list, and just checking whether any of the elements in the first list are 1, which is totally valid. That's a good way to do it. But for now, just for clarity, we'll just do it for both of them. And if you want to implement this optimization yourself, that would be cool too. Cool. Now all we need to do is iterate for this index I in the range 0 to 3. And all we need to say is if list 1 at this index and list 2 at this index, then we can return false. Why? Because if this character is located in both this one, the first list and the second list, then that's bad. We should return false. Else, if all of these indices are okay, then at the very end of the for loop, we can return true. And okay, so we have this is good position. And remember, the final thing is we have to count. We can't just return all these. So let's account for that. We can move this down. And we don't just want to check is good position. We want to say if is good position, then we can add 1 to our final answer, right? Because then this is a good position. So we can say answer plus equals 1. This just means add 1 to the answer. We should initialize the answer actually. We should say at the beginning, the answer is equal to 0. And then at the very end, we should print answer. Yeah, so that's it. This is our code. Just to go over it again, you're going to want to read the input into a list of strings. Then we're going to start at 0. And then for every single position, we're going to say, are you a good position? And if you are, we can add 1 to the answer, and then we're going to print the answer. But how do we figure out whether it's a good position? We're going to want to create an existence list for the spotty and the plain cows. And we're going to want to go through this list and see if any conflicts occur. And if you have any characters that are in both the spotty and the plain cows, then you've got a problem and you should return false. Otherwise, then this is going to be otherwise this position is going to be a candidate for determining whether something is spotty or plain because you have no conflicts. Hopefully this makes sense to everyone. Any questions? Okay, nice. I'll leave this up for one more moment in case people want to just look it over or write it down. But at this point, if you're good with this implementation, let's fire up MIT App Inventor and we can see how to code this up in practice. So I will create a new project, and in a few moments, I'll start sharing my screen and we can write the solution up together. Okay, so I think everyone has probably had enough time to look at this. I'm going to start sharing my screen. Let's see, how do I share my screen? Google Chrome, MIT App Inventor. Cool. So I hope everyone can see this. It's just my, oh wait, I think I should share my entire desktop. Yeah, let's just do that. Huh. Cool. So this is my desktop. Give me one moment while I do something. Cool, and I've also pulled up the our pseudocode, so we can look at this while we code, possibly. I don't know if this is going to be helpful. All right, so we have our pseudocode on the side, and you know, we're working with this. First thing we need to do is we need to set up some components where we can read in our input. So let's give it a text box, and let's give it a button for the text box. I just like making these full width. Oh, and by the way, I hope you're following along with me. I think it would be nice if we could all code this together and you could give me suggestions for how to implement things. So we'll just say button solve. This will be our button. Always remember to name your things, name your variables appropriately. And we should just say like text box input. And we also need to put a label to print the output, right? So we should rename this to label answer. And we're just going to say answer goes here. Nice. I'll also make this full width. Let's say button just says solve. All right. I hope everyone's following along actually. And if you haven't opened up MIT App Inventor, I'll give you a few moments to open that up while I set up my emulator so you guys can see on my phone what I'm doing. So I'm going to pause for maybe like a minute or two. Please pull up MIT App Inventor and get to where I'm here, where we have all the inputs. Put USACO input here. And we should make this multi-line. So yeah, feel free to just take a few moments to get to this point, and then we will resume in like a minute or two while I get this thing set up. All right, so hopefully this has been enough time for you to set up everything. I'm gonna have MIT App Inventor pulled up. And then here, let me go ahead and just scan this so we can make sure that our thing is working. Scan QR code. Okay, taking pictures is fine. So what I should see is we have this user interface, which is cool. And we have this thing that says, put USACO input here. Let's see what the USACO input should be. I should probably send this to myself so I can load this up. So let me do that. Let me copy paste the input and we'll go from there. Cool, so I'm on the USACO website. I can just copy the sample input and throw it into MIT App Inventor. Copy, go here, paste. So as you can see, everything's gonna be fine. Usually, you probably need to make sure to click the multi-line option so you can have multiple lines, but I'm gonna have this, and when I hit solve, obviously nothing's gonna happen right now, but we're going to code up the logic to solve the problem.
Yeah, Kevin, there is another way you can paste the input to the text box in the property.
Oh, actually, that's pretty smart.
Yeah.
Okay. Yeah. Okay. Okay. So the other solution is you can just take this, and you can put this into text. So when it loads up, it'll just show up like that, as you can see here. This is a lot smarter than what I was doing. Cool. So yeah, you guys should do that. All right, so let's go into our blocks. We should start writing the logic. So I think the first thing we need to do is make a callback for the solve. So when we click solve, we need to do something, right? This isn't necessarily an exercise in software engineering, but let's try to make our code as nice as possible. We're going to want to create a list, right? Let's create a variable, and we're going to initialize a list of strings, and we're going to read the input into these strings. So let's just say that this is going to be, and if you look at our pseudo code, what we said was we want to have this variable called genome, and we're going to read the input into it. So let's call this genome. And we're going to initialize it, let's just say, to an empty list. So yeah, let's, yeah, okay, cool. So what we actually need to do is read in the text from this label answer. We're going to want to grab the text. And to read this in very easily, actually, one of the smarter ways you can do it is you should just read in the entire string and then split by the return character. So in computers, there's this thing called a return character that looks like this. It's \n. And what it does is it signifies a line return. So at every one of these lines at the very end, there's a \n. So we can get the text and then split it by the return character to get every one of the lines independently. And I have no clue how to do that. So let's see. Okay, we have split text. We want to split it at the return characters, and the text is actually just going to be the text that we get from the label of the answer. And let's initialize genome to this. And just to make sure everything's going all right, let's go to our text box, our answer label, and let's just set the text to this. Let's just set the text to genome and see what we get. Cool, so I'm gonna hit solve, and it just says, oh, this should be not label answer. We're gonna wanna grab the thing from the text box input. So we're gonna grab the text here, and nice. So we get an array. This is clearly array notation where we have every one of the things independently. But obviously this first line is just some metadata about our problem and we don't really want it. So what we want to do is we want to extract the information from the metadata and then delete it from this list. So let's create some more variables because we want to know what n and m are, right? So we can initialize two variables. We have an n and m, and we want to initialize it to what? We're going to want to get our list index select list item. We're going to want to select the 0th. Oh, is MIT App Inventor 1 index? It might be 1 index. So we want to select the first index in this array, which is going to give us the 3, 8. And we know that it's going to be according to the input format. The first line of the input contains n and m separated by a space. So we know that when we split it, there's only going to be 2 things. So we want to split. We're going to want to split the genome. We're going to want to split this text at the space. We're going to want to put a space in here. So then this is going to give us this is going to give us a list of 3 and then 8, just a list of 2 elements. And we're going to want to turn these into numbers. So probably what we should do is initialize a third, or initialize another variable, local variable. This is going to be a temporary variable. So temp nm, it's going to be this thing. So it's going to give us a list. And so then n is going to be the 0th the 0th or the first index. So we're going to select the first index of temp nm, and then we're going to have m be the second index. So what this is going to do is it's going to take the 3 and it's going to stick the 3 in n, and it's going to take the 8 and then stick the m in, the 8 in m. These actually give you strings, so maybe we should convert them into a number. I don't know if we can do that. It might be in text. Okay, let's just Google this. MIT App Inventor converts string to number. Oh, a number presented in a text string will be considered a number and not text. So Leo is right. It might be just automatic. Oh, 5 plus 4 is 0. Okay, it's 9. Okay, good. Okay, nice. We'll just roll with that. Let's just hope that this is right. Cool. Nice. Oh, also they have like a cool thing where you can like add 0 to your number to just make it explicit. I don't know. I like to make things explicit. So let's just do this. We're going to add 0 and make sure that they're actually numbers. Cool. So now we have n and m. And the final thing we should do is we should delete from genome. We should delete the first element. So let's remove list item. We can delete from genome. We're going to delete the first thing. Okay, so now let's set the label answer text to genome, and let's also print out n and m. But let's see what genome looks like first. So we click solve. It's going to give us A, A, T, C, 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 A, T, all the way down 1, 2, 3, 4, 5, 6. We have 6 things printed out. That's good. That's what we wanted. And let's also set the label text to, let's see what n looks like. So n is going to be 3, and m, if we solve, it's going to be 8. Awesome. So we have our input parsed. That's honestly sometimes the most annoying part. So now we have genome, n, and m. So why don't we just solve it? Let's create a procedure. Let's call a procedure that says solve. So to solve, we need a couple of arguments, right? We need n and then m and then this list. Let's call this nm genome. And all we need to do here is call this procedure. So let's call it. I don't know how you call procedures. Maybe procedures. Okay, we can call solve. And then we pass in these variables. So we can say n, and then m, and then genome. We just pass these variables in, and they're all nicely parsed now. Cool. I imagine it. Okay, we'll just roll with this, and then I might write I might write a few other helper functions in the future if I find things kind of annoying. But let's solve it. So let's look at our pseudocode actually. What is our pseudocode? We said to solve, we first parse the input. Okay, so we did that. We initialize an answer variable, and then we iterate through all of these, and then we check. So let's do that. Let's literally just write it out. And this is something I like a lot about MIT App Inventor. It's literally just pseudocode, and it's very straightforward. So we have answer, we initialize it to 0. And then eventually what you want to do is you're going to want to set the label answer text. You're going to want to set it to the answer. Get answer. Cool. But what do we need to do in the meantime? We need to make a for loop. I have low-key forgotten. Okay, there we go. That's a for loop, but it's in the wrong place. So let's make a for loop and let's iterate from 1 to m. How do we do that? Well, very conveniently, we have m here. So we go from 1 to m, and then we're going to say, is good position. And if it is a good position, we'll do something. And if it's not, we'll do something else. So is good position should return a value. And apparently in MIT App Inventor, you have to do like, use this weird thing to get the result out. Okay, yeah. So let's just define it for now, and then we can change it later. Is good position, and then we can call it. We can say is good position. Now we need an if statement. We need to say if is good position, then we want to add one to the answer. So how do we do that? I think we have to get a setter, and we can set answer to answer plus 1 plus add. Okay, I don't know what I'm doing. Math, add. We have to do get answer, and then we want to add 1 to it. Cool. So we're almost done, actually. We just need to write this is good position function. So what is good position? It takes in an argument. So we forgot about that. We need to give it an argument. This argument is just going to be position. And what is this position? Well, it's going to be POS up here. It's going to be our for loop. So let's pass in the position. And that's all it needs to do. Cool. All right. So I will be honest with you. I don't actually know how this should be structured because it's got like this weird, I don't really know how to catch these returns when you return them in MIT App Inventor. So let's see if there are any cool things we could do. Ah, okay. Huh. So there's a do result. There's an if then else. And
I'm pretty sure what you're supposed to do with the do result thing is that you define a local variable, the second type of block, and then you just put the do result inside that, and then use the local variable as the result.
Gotcha. Wait, so you're saying we can define a variable like this and you can use this variable in the result?
No, put it outside the do result and use the second type. There's one that has like the pluggy thing.
Oh, like this?
Yeah.
Okay,
and then you can use it there. And then you remove that.
Okay, awesome. Much appreciated. Cool. Yes, even I am learning things. I don't know how to do these things in MIT App Inventor because in programming languages, stuff like that. But thank you. Cool, so now we can do things. Okay, awesome, this is great. All right. So I am still trying to get familiar with this. Let's just roll with this. I don't know what I'm doing, but let's just see. So we want to do something. We want to create these two lists and we want to compare them. So let's just keep writing things out. Let's create two variables. We want to make a list and a list. So we have list 1. So let's call this something more descriptive. We have spotty and we have plain. And we're just going to initialize them to another function, which is just create existence list. Because this existence list will basically tell us, well, the list. I'm going to leave this argument a little bit vague for now, and then we'll come back to how we want to structure the argument. But yeah, cool. Let's see, what else do we need to do? So we need to get this existence list out. So we need to call existence list. We're going to get the existence list. And then we're going to want to iterate through all the 4 positions and see if any of them are conflicting. And if they are, we're going to want to return false. And then otherwise, we're going to want to return true. So now we need another for loop. We need for each, let's just call this an I. Let's move this out. For each I from 1 to 4, we need to see whether the existence lists are in conflict. So let's do that. Let's go and say if the list item is equal to, if list item, we have logic. And so if you have this list item, which is in the spotty list, if we have index get I, oh, it doesn't like that. We'll just hover then. Get I, and in the plain list, you have I, and if they're both true, then we're going to want to do something. We're going to return, we want to return false. So we'll just call this result, and we'll initialize it to some random thing. You might just say false. And then I'm guessing what we want to do is we want to set the result to if they're good or if they're the same, then we can just do false. And actually we can just default to true actually. And cool. I don't know if this result is actually necessary. Maybe we just want to return the result here, but maybe we don't even need it. Yeah, we'll just do this. And so if you see any of these cases, we're going to set the result to false, and we can actually break out of the loop. I'm not going to bother doing that because it's just 4 things that we have to do. And if we don't see any of these conflicts, then this code is never run, and then the default is true. So then we're going to return true. So that's good. This is literally all we need in is good position. And the only remaining piece of the code is now we need to create existence list. And then we're done. So let's clean up the blocks and let's continue. So just to recap what we've done so far, we have solved, this is going to be parsing the input. This is going to be solving it by going to every position and seeing if we have a good position. And then if we do, we're going to add one to the answer. And then in is good position, we're creating 2 existence lists, and we're going to check whether the existence lists conflict. And then if they do, we're going to return false. Otherwise, we're going to return true. And then now all we have to do is create the existence list. So the existence list, there are a few ways we could do it. Like here, I decided to pass in an argument for spotty or plain. But I think that a better way to do it probably would just be pass in the array that you want to create a list of, and we'll give it to you. And so we would have to slice the array. If we wanted the spotty ones, we would have to slice the first n. And then if we wanted the plain ones, we would have to slice the last n. Let me see if there's any easy way to do this. Okay, there's not. Then maybe we shouldn't slice. Cool, and we'll just pass in an argument. So in is good position, I've actually forgotten to do something. I've forgotten to put in the genome because we need the genome to actually do anything. So let's pass in the genome as well. And in create existence list, we're going to have to do a few things. We're going to need a few arguments. We're going to need the position, obviously. We're going to need the genome, and we're going to need another thing. This is going to be genome. This is the position. And this one is spotty, right? We need to tell it, are we looking for the spotty cows? Or are we looking for the not spotty cows? So let's fill in these arguments. Our genome is obviously just genome. Our position is literally just a position. And I'll duplicate this in a second. But is spotty for the first one is going to be true. And then once we duplicate it, we'll just make it false. All right, great. So now we have our existence list created with all the necessary arguments. All we need to do is create the actual existence list. So it's going to be true, and this one's going to be false. So in our existence list, we're going to need to return this thing. We'll just call we'll call this list the list. We're going to initialize it to make a list. We have A, T, C, and G, right? So how many do we need? We need 4 elements. And we're going to set all of them to false. Awesome. So now what do we do? Okay, and also we'll just return result is the list. All right. So what do we need to do? We need to iterate through all of the things in the genome at our position, right? And then we're going to set all the indices to true or false. So there's something that we need to do is we need to map the indices of this list to A, T, C, and G. And a nice way we can do that is we'll just make a global variable, and we'll say this is a DNA to index, and we're going to create a dictionary. So we're going to make a dictionary, and we're going to make this really simple. All the keys will be the characters, and all the values will just be indices. So the key here will be A. Oh, what the heck? Okay, so this will be A. This will be T. Oh, it doesn't like the last thing. Okay. C, G, Oh, wait. Okay, HECG. And what is the value? For the first one, it's just going to be 1, right? Because we want the first index. The second one will have 2. The third one will have 3. And the fourth one will have 4. So at every position, we can just take the thing in the string, and we can throw it into this dictionary, and it'll tell us what index we should be editing. This is really nice. So we have this dictionary here, and what do we need to do? We just need to iterate, right? We need to iterate for the cow. Let's just call this cow index, all the way from 1 to something. Now we'll talk about what this is later, but let's just assume it is spotty. If it is spotty, then we just need to iterate from 1 to n, right? So we actually need n. It's another argument we've forgotten. Let's just put it here. We need to pass in n. And then if we have n, we can iterate from 1 to n, and then we can get all the cow indices out. But we're not actually there yet. Well, first of all, we should change this to be correct. We should pass in n. So what this means is here, we also need to pass in n. We need to go backwards and add all our arguments that we need. So then here we need to pass in n. Oh, we don't want the genome. We can pass in n. And then now we should pass in n. Cool. So now we have all our arguments set up, and now we can iterate all the way through n. Now this is actually incorrect. Let me put a thing here. This is incorrect. We'll come back to it later, but does anyone want to tell me why this is wrong? Just going from 1 to n? If we always go from 1 to n, why is this wrong? Yeah, exactly. It'll always track spotty cows, and we're not actually using this argument. But I'll first build out the code for this incorrect thing, and I'll come back to fix it. It'll be a really easy fix. Let me check my messages. I think I'm getting a few other messages. Okay, yeah, I can definitely go back up. Does this help? But yeah, it'll always check spotty cows. That's exactly why this is incorrect, but I'll come back to fix it. All right, let's keep going. All right, so this is incorrect, but let's just roll with it for now. We're going to want to go to every single cow index. Remember, we're going to want to go to every single index. We sort of lost the explanation here, but here it is. We're going to want to go to every single one of these indices, right? And we're going to say, let's look at A. Let's put it in the array. Let's look at G. Let's put it in the array. Let's go to G and let's put it in the array. So we have to make it very clear how we're indexing things. Remember, indexing is done first by row, then by column. So should cow index, is cow index indexing the rows or column? Does anyone want to throw it into the chat which one they think it is? When you go from 1 to n, is this columns, or are you indexing the rows or the columns of our thing? Yeah, exactly. So Jefferson, Ambrose, Leo, all got it right. We're indexing the rows. And then POS, position, is actually indexing the columns. So we should be doing it in that order. So let's do it in that order. Let's create a new local variable just to make things clear. This is the current DNA, cur DNA character. And we're going to want to initialize it to this. We're going to select the list item. We're going to select the cow indexed list item in the genome. So this will give us the entire slice. This will give us, you know, an entire slice that goes row-wise. This will give us all of these. But now we want to get to position. So at position, we're going to go to position 5, for example, and then we're going to slice down. And so the exact thing that we're going to be looking for is going to be this C right here. And how do we do this? We just need to go to the string and get the positive index. So then we'll want to go to the, we're going to want to go to the string and get the character at index pos. I don't actually know if this is possible. I know you can select list item and then we can convert a string into a list, I'm guessing. Or maybe this will just work. Okay, let's just hope that this works. And if it doesn't, we'll see why. So then we can select the list item out of this list. And then we're going to want to get the pos. So this should give us the index that we want. Pos. So this will give us the specific character that we're looking at right now. And all we need to do is go to lists and we can set the index at list. So we can, okay, so we can replace list item. We can go to this list here. We can get this list at the index that is, so which index do we want? This actually is important that we have this DNA to index thing, because we can go to our thing and we can look up the value. We can get the value at the key. The dictionary is this. And the key is just going to be our current DNA character. So we go to the dictionary, we're like, okay, I have a C here, that should be index 3. So we're gonna go update index 3 in this list to say that we found a C. And then we're gonna replace it with true, right? Because we found it. And eventually you just do this and we should, it should work. I think this is gonna be a valid implementation as long as this part holds up. I'm not sure if this is right, but let's hope it is. Cool. And if it doesn't, we'll just debug and it'll all be okay. But so now we have to come back and say like this cow index thing is not quite right because we're always going to be looking at the spotty cows if we go from 1 to n. So the easy way we can do this is to make an offset. Let's create an offset. This offset is going to just be offset. And we can say that it's going to take on a certain value if it is spotty and then take on another value if it's not spotty. So for this, I think we can use this cool if-else pluggy thing. So if it is spotty, then what should our offset be? Basically, and just to define an offset is going to be a value that we add to every single index. So if the offset is 1, then we're going to go from 2 to m plus 1. If the offset is 5, we're going to go from 6 to m plus 5. What should our offset be if it is spotty? If we want the spotty cows. Maybe I didn't explain the concept of offset too well. Okay, so we have an answer. Yes, this is exactly correct. It's 0. Because if it is spotty, then we don't want to offset anything. We literally just want to go from 1 to n. But what if we don't want spotty cows? Then what should our offset be? Yeah, exactly. So Jefferson is actually not wrong. You're not wrong because the example that was given in the USACO site, the answer is correct. Like you just want to offset by 3, but in fact, n equals 3. So the more general and correct answer would just be n. And we can say that we can set count index to the sum. I don't know if this works. To the sum between count index and our offset. So this is like a really just clean way of saying, if it is spotty, we're going to look at a certain portion. And if it's not spotty, we're going to look at another portion. So yeah, I mean, you know, I think we're done. I think we're almost done. There might be a few bugs in this code and maybe we'll find them, but I think we're done. So let's test it out. I don't know if it's gonna work, but let's keep our fingers crossed. I think my screen sharing thing has been interrupted, so let's reconnect. Yeah, Dylan, I kind of agree with you. This is a little bit complicated. It's quite a bit to just grapple with, especially if this is your first time seeing these kinds of problems. But I promise you that it gets much better. The more practice you do, the better you get. I was in the same position as you were only like 4 years ago, and you just have to do lots of problems, and then eventually, eventually it gets a lot easier. But if you have any specific questions, or if you just want me to go over it again, I will. I can just in a moment. But let's see if this thing actually works. Why does this thing want my microphone? What? Okay, so it's connecting. Okay, nice. So it seems like it worked. We'll go to MIT App Inventor. I don't think it's still connected, so let's reset the connection. Okay, let's scan our QR code and see if it worked. Fingers crossed. Okay, so we have this. The answer goes here, moment of truth. If we click solve, yay, okay, it failed, nice. So what happened? Operation select list item cannot accept the arguments, something. So where does this even happen? Huh. All right. So where do we do this select list operation? So I think we know that all of this code is okay because we already tested it. So we can eliminate this from the candidates. Where else do we do select list item? We do select list item here. Where else do we do select list item? We do it here. Now, if it were me, I would sort of guess that this is the culprit. So let's do something. To debug things, a very easy way of debugging things is to use a notifier and print everything out, just so you can make sure everything is going okay. So go to the designer, go to the palette user interface, go to notifier and drag one in. This will allow us to print out all of our code, to print out all the things that are going through our code just to make sure things are all right. So let's go through here and let's make sure everything's all right. Let's print out the current DNA character, or maybe even beyond that. Let's print out the genome. Let's print out the genome and make sure it's all right. So we go to our notifier and we can show alert. Let's show the genome. Let's make sure that the genome is actually correct. So we have so actually the alert was shown before our notifier actually went off. So let me just do this again. Okay, so we have this. So our genome looks correct. So that's good. Now let's make sure that our current DNA character is actually just a DNA character. So solve. Okay. So this is where the error is. We've identified it, right? Because in the previous cell, we ran it and it was okay. And then here, when we showed the alert did not show up. So that tells us that the error is in here. So what's wrong with this error? Let's see. Our cal index is just going to be an index. And then we're trying to get the position of some list item. So I think, I was talking earlier about how I didn't think this was going to work. I think this is the problem. So here's what we'll do. Instead of printing out the genome, let's print out this. Let's print out the genome at the current cal index. That should probably tell us, that should give us some information. So it gives this, right? So it gives AATCCCAT. So that's good. That gives us a string. Now we want to go to the string and get the index. Now this is where things get complicated, right? Because this is a string and we're trying to select list item in the string, which is bad. That's not what this API is used for. So let's Google this. MIT App Inventor get string index. I actually didn't know how to do this. Okay. Compare text starts out contains split at first, split at any segment, replace all. So I don't think any of these things do anything I want. So maybe another solution might be you turn a string into a list. So turns MIT App Inventor. And if any of you know how to deal with strings, please let me know. Like I have no clue how to use strings in MIT App Inventor. Oh, you can use this. Oh, sorry, go ahead.
So yeah, you can just use split it by an empty string and that separates everything.
Okay, awesome. Thank you very much. Great. So hopefully once we fix this, everything will be fine. So we're gonna go here and instead of, oh, what is this? So instead of doing this, we will split by an empty string. And that'll give us a list. Cool. All right, so we're splitting by an empty string. This should be fine now. Let's hit solve. Oh, okay, so dictionary lookup cannot accept the arguments this. So we're trying to pass in our cur DNA character and apparently it's not happy about that. So let's see what our cur DNA character is right now. So now we'll just go back to our notifier and then show an alert. Let's just show our DNA character, what's being spit out by this process. So it shows an A. So A, that seems correct to me. So it's, you've got A and then global DNA to index is that, and then if not found is that. So what's the error? Let's take a look at the error again. Lookup cannot accept the arguments A, blah, blah, blah. Not found. Huh. Maybe recursive lookup is not what we're looking for. Maybe we should just get value for key. So key path might be some kind of like other complicated thing. So I think this will be right. Oh, okay. So our thing spits out a 1. So this is in fact the correct answer for the first case. But I don't trust myself. We should try this on more cases. So what we can do is we can go here, return to the problem list and download all the test data and we can test it on a bigger thing. So let's open the zip. Let's go to the second one. Let's open both of these. Okay, go to Sublime. And here, we can drag these in. So this sample input should return a 4. So let's go to MIT App Inventor and stick this in. Let's see what it says. This should return a 4. Oh. Okay, so hopefully what you see on the screen is now we have this new input. Let's see what happens when we hit solve. It says 4. Okay, great. Let's keep going. Let's just really try to make sure that everything is okay. So we have Sublime. Let's drag this in. This is a larger input. So we'll paste this in. So we have a new input here. It's 510. Let's hit solve. And the answer should be 2. Is that right? Yeah, it's 2. Nice. So at this point, we're getting fairly confident that our thing works. Let's try a really big one. Let's try a 426 bytes. This one is going to be 10 by 20. So this one's pretty large. Let's run this one. 10 by 20. Solve. It says 9. Is that right? It says 9. So it's looking pretty good. I think this is definitely, or it's probably correct. Here's a 4 by 100. Let's see what happens here if we paste all of these in. So we have this huge thing. We're going to hit solve and it's going to say 50. Is that right? And indeed it is right. So I think our solution would probably pass all the test cases. I haven't done all of them, but I did all the big ones and they all look correct. So I think we're good. So yeah, that's pretty much it. That I hope that this made sense. I don't know. Before I conclude, I think I should ask if anyone has any questions. If anyone wants me to look at their code. But I hope at least some of you were able to fully implement it and see that it works. So if you have any questions, feel free to throw it in the chat. I'll give you a few seconds, and then if there's nothing else, I'll probably just conclude. And I know it's a Friday night on a holiday weekend, so I'll let you guys go ASAP.
Thanks.
Okay, does MIT App Inventor have its own separate coding language? So the answer is no. I think MIT App Inventor can be considered its own programming language, I would guess. I think under the hood, they're using Java or JavaScript or something, but you can't see that. It just stands on its own. I think it's nice in the sense that if you think about the pseudocode that we wrote here, we basically converted it directly into MIT App Inventor. Like, it looks very similar. The only difference is that our create existence list was a little bit more complicated. But if you look at, for example, solve looks pretty much exactly like our pseudocode. We just made a variable, we iterated through everything, we just added one. And the nice thing is that you don't have to remember all the syntax. You can focus on thinking about how to solve problems and how to structure things. But once you're comfortable programming in MIT App Inventor, I think you'll be ready to tackle your own full programming language. But yeah, I think it's nice. It separates the syntax and the thinking. Yeah, cool. So I'm pretty sure this solution will be published somewhere on the gallery. But I hope that, just to recap, we've done a lot, right? We've looked at all these kinds of different approaches to the problem. We've talked about analyzing your algorithms in terms of worst case and best case performance. And then we've written this code that we tried to keep clean. We created a bunch of functions that kept our code very nice and modular. And I think overall, we covered a lot of interesting, useful tricks that you might use in the future when you're solving these kinds of problems. And I just hope that they're helpful. USACO is definitely only one of the very first building blocks towards being able to build interesting things and useful things. But I think it's very important. I think being able to think about these problems and structure your code in a clean and nice way is super important. And it's something that I'm still learning, but USACO does a great job at introducing you to this problem. That's pretty much all I have for you today. I hope it was interesting. I hope it was fun. And thank you to you all for teaching me things that I didn't know, especially about MIT App Inventor. I think it's always fun when I get to learn from you guys. But yeah, I hope you guys had a nice holiday weekend, and I'll see you guys around.
Bye.
All right, thank you, Kevin, for this awesome presentation. It is like a master class. I haven't seen this awesome kind of presentation for long. And for all the students, if you can stay this late, that means you really have a great characteristics that you can achieve much higher. All right, so thank you everyone, and have a great weekend.